Hello, this is Professor Paul Guyad, and today we're going to be talking about data structures, particularly the binary search tree. So I'm going to go ahead and share my screen so we can start constructing the binary search tree and seeing just what this data type is like. So the binary search tree has a root node, and the root is at the top. Usually we think of trees, the root's at the bottom, but here it's like kind of like an upside down tree. So the root, there's one root and if there is one, and we're going to have a binary search tree of integers. So I'm going to give this root node a value of, like, uh, oh, sorry, 16, right? And then I'm going to create other nodes. So now we're going to start going down. It's binary, right? Binary search tree. So there's a left and there's a right. So this is the right subtree. And in a binary search tree, in a valid one, at least, all of the elements in the right subtree are greater than the root. And all of the elements in the left subtree are less than the root, while conforming to the principles that the right subtree is greater than, even within the subtree, and the left uh, node to the left child is going to be less than the parent. So right now the root is the parent of this node right here. And then I'm going to create a couple of more nodes to create a three-level binary search tree. So there's the right subtree, and then let's create the left subtree. And then of course there are um, edges to connect the tree. So this tree has four leaves, and then let's keep assigning values. So we said that every node in the left subtree, so over here, is going to be less than the root, which is 16. So we can make this like 13. And then this node, the right child of the 13, is going to be greater than 13, but less than 16. So it has to be either 14 or 15 because each value, that's another principle of binary search trees, each value is unique. There are no duplicates within the binary search tree, which makes it all the much easier to search for a value, right? It makes it a very valuable and efficient data structure for search. And then um, the left node, the left child of the 13 should be less than 13. So we'll make it like 11. So far, this binary search tree is valid. Now we go down the right subtree, right? And this has to be greater than the 16. So we'll make it like 20. And then this one here, the left child of 20 has to be less than 20, but still greater than 16. So we can make that like 19. And then we can make this any number greater than 20, right? So we could make it like 22. So right now, this is a valid, um, this is a valid binary search tree. So we'll just keep that sitting there, right? So each node in the right subtree is less than the root, and the root is 16. And each node in the left subtree is less than the root. Okay. So this is valid. Um, Now let's construct a binary search tree node in Python. So I already got it started for us. You start with class BST node, and it has three attributes. So we do a def, init, we do the constructor in Python, the init function, and it goes self, the value of the node, and the left child and the right child. So we would do self dot value equals value, self dot left equals left, and self dot right equals right. So if I was constructing the root node, right, if we go back to the paint, the diagram, it's 16. So root would look like this. Root equals BST node, and then its value would be 16, and its left child would be a BST node, right? What is its left child? 13. So BST node 13, none, none. Sorry, so these should be initialized to be none. And the right child of the root is 20. So we would do another BST node, 20 is the value, none, none. So that would be like a nice way of coding the root node of the binary search tree that we just drew in that diagram. Then what methods you would want to construct to start out with the binary search tree, which are very useful and why we have this data structure in the first place, is search, right? So the ability to search a value, you're given the root and the value to be searched, and you're trying to determine if that value is within the tree. And because every value is unique and the way that the values are organized in the binary search tree, every right child is greater than the root and every left child is less than, the root, more or less, right? That being the structure, its search is made to be pretty efficient in the binary search tree. So I'm just going to write the signature for the search method, and then you can kind of take that to the next level and try to discover. It's a recursive method that you would want to write, so that makes it even more efficient. Um, so right, just putting the facts recursive. Yeah. So this has been a presentation about let me stop there. This has been a presentation about the binary search tree data structure. It usually comes after linked lists, stacks, and queues in terms of when you would learn about it. And it gives you a good idea of, a nice data structure for searching um, for values, the way that the structure is set up of the data structure. So thank you again. This is Professor Guyad, and have a great day.